started.
So Bernie's Jewish. Bernie's like, way.
Okay, so we already know half of this lesson, okay, but we're giving it the formal theorem called fundamental theorem of calculus. So there's two parts to it. One is we're going to do the derivative of the integral, and then the other one is we're going to do the integral. Well, no, we're going to do the integral and then work our way backwards where we evaluated with the limit of top and the bottom. Okay, so first we'll start off with part one. Okay, so remember I said derivatives and antiderivatives are inverse operations like addition and subtraction, multiplication and division. All right, with some slight variations. Okay, so first thing, we always have to make sure it has to be continuous. If it's not continuous, we can't find the integral. So take, for example, 1 over x. What's 1 over x look like? Like this one? Yeah. Okay? Sure. So I can find the integral from, let's say, 1 to 3. Right? 1 to 3. I can find that area under the curve. But I can't find from negative 1 to 1. Right? So this would not be that would not be defined. Okay? So that's the first thing. We have to make sure it's continuous. So then it's going to have a derivative at every point such that the derivative of the antiderivative gets back what our original equation was. Given the top limit of integration has to have a variable, usually they have x in there, and the lower limit of integration must be a constant. Okay, so let's just take an example. Let's start with an integral from, we'll say 3, let's say 3 to t of t squared dt. Okay, so I'm going to use, you'll see here also, there was a little confusion when we used t and then x. Hopefully this will clear that up. What happens when we integrate t squared?
T.
Wait.
No,
t to the third over 3.
T to the third over 3. Evaluated from, actually I did want to have this as an x. Sorry about that. This should be an x. Well, I wanted to make it so the lower limit was a constant and the upper limit was an x. Okay, now what are we going to do? We're going to evaluate it. So what's that going to look like? This is going to be third over 3 minus 3 cubed over 3, 9? Okay, so now what if we did the derivative of that? So if we take the integral, we get x cubed over 3 minus 9. And now, what happens when we do d dx of this? You get 3x squared over 3,
x squared.
Which is x squared. And what happens to the 9? It goes to 0. So that's why that's the same as t squared, just with a different variable. So what we are going to do here is when we apply the fundamental theorem of calculus part 1, notice it's still f of, but we're going to replace the t with an x. The lower limit of integration can be any constant, right? So I could have made that 0, I could have made it 1,000. What will always end up happening? When I do the derivative, it'll go away. It'll be 0. Okay, questions? Make sense? Okay, so we want to find dy dx. So I'm going to take d dx of the integral from 0 to x, 1 over 1 plus cosine of t dt. Now, right now, I can't integrate that. We don't have any methods currently to integrate that by hand. But we don't care because we're doing the derivative of the antiderivative. There's no work to do here. 1 over 1 plus cosine x. We're just replacing the t with an x. That's it.
I did.
That's it.
You know the whole lesson.
Right, so no matter what, if we were to, anti-differentiate this, as soon as we go and take the derivative, we're just going to get back what we started with, but with the new variable. And the 0 on the bottom doesn't matter, because ultimately when we do the derivative, it's going to go away. All right, so same thing here. When we do d dx, and also if you want to just write dy dx equals, that's fine. I'm going to write it out so you can see. This is going to become x minus 2 e to the x. Is this hard?
Wait, so we can go straight to the answer, right?
Yeah, you could just write dy dx equals if you want. Okay, now that was really straightforward because the lower limit of integration was a constant, upper was just x. However, if you have something in your upper limit of integration other than just x, like an x squared or negative 2x, you have to apply the chain rule to the upper limit of integration. So we're going to apply this, bless you. So we're going to apply it to the upper limit of integration. Okay. So it's going to operate pretty much the same way. We're going to replace t with x squared and then multiply by the derivative of x squared. Okay, so we still have to kind of compensate for that if we have that composition of function in the upper limit of integration. So this is going to become tangent x squared over x squared times 2x. And then we'll just put the 2 in front. So we'll make that 2 tangent x squared over over x. Right?
Yeah.
Right? If I have an x to the first power over x squared. Yeah? Okay, that's it. That's all we can do with that. All right, so are we okay if I just go right to dy dx this time? So again, all the u's are going to be replaced with
Negative 2x.
negative 2x. And then what do we have to multiply at the end? Oh, I skipped a step, so I didn't feel like writing out the setup. I was just mentioning earlier, you can do that. So we'll have negative 2x sine of negative 2x times negative 2. So what do we get? Okay. Now, someone in the other class also asked if you could take that negative out in front because sine is an odd function. You can. You don't need to, though. You did that? Yeah. So that's, if you wrote negative 4x sine of 2x, it's the same thing. You just don't, it's not necessary. Okay. Last 2 examples, and then we'll do part 2, fundamental theorem of calculus, which we've actually already done. So something happens here. Here, the lower limit of integration has the variable, and here, these 2 both have a variable. So let's tackle A first. What would you do? Okay, so we know that we can flip the top and the bottom. Good, so this is just like the very first ones we did, just it's going to have a negative in front. So we'll have negative 3x
natural log x. Right? That'll be my dy dx.
Okay. Last one. So we have a 2x and we have an x squared. Any ideas? Has to do with the additivity property of integrals, where we can actually split up an integral into two parts. So thinking about this function, I want to introduce just any constant, any number that this can be evaluated. So I wouldn't separate it using a 0 or a negative number. I could use like 1, I can use 2, I can use 100. It doesn't matter.
Just maybe we'll say 2x to, I don't know, let's use 3, just because. And then the next one. So I want to pick some positive value so I can separate this, because I can only have one variable in my upper limit of integration. I can't have two. So what I'm going to do is I'm going to introduce some number here. It doesn't matter. 3 is just a placeholder. It doesn't matter. This can be any number as long as it's not a negative number, because that wouldn't make sense in the context of this problem. All right.
How do we know x squared is bigger than 3?
Okay. Here's the beauty of integrals. It doesn't matter. It will work out whether it's bigger. We don't know if x squared or 2x is bigger, and it doesn't actually matter. Okay. Because regardless, it'll work out in the end. So even if we have limits of integrations that are switched around, it makes no difference.
So you want the opposite figure, like times 9.
If it's larger, then we would switch it. But we don't know. We don't know what's bigger.
Yes, so how do you know the right
It doesn't matter.
-1.
So it doesn't matter. I mean, we could do an example. I can show you. Because what ends up happening is when we subtract, trust me, you'll still get the same end result in the area under the curve. Yeah, we're going to flip the first one around. So I'm going to make this negative 3 to 2x natural log of t dt under the radical. And the second one I'm just going to keep the same. Okay, so my dy dx will be what? So the second one already had the variable in the top. You always want to make sure the bottom number is the constant, because this constant is going to ultimately go away. Okay, so this is going to be square root of natural log 2x plus square. Oh yeah, times 2. Thank you. Plus square root of natural log of x squared times 2x. So I have -2 natural log of 2x plus 2x square root of natural log x squared. Okay, part 2, we've actually already done. We just used it. We did this in the last lesson where we had something like this. And then we said, oh, that's going to be equal to f of t. And then we evaluated from f of x minus f of a. This is the same exact thing. This is just what we call the part 2 of our fundamental theorem of calculus. So again, f is continuous. F is an antiderivative of f prime. So when we integrate, we get f of x, and so we do f of b.
b minus f of a. So this whole next part is going to be what we've already done. That's why I said it's okay. And we want to be able to evaluate these without a calculator. Okay. All right, these would be no calculator problems. So let's start off. What's the first one? What do we get? We get 4x plus 2x squared over 2, so that's x squared. We want to evaluate that from 4 to 6. Okay, so we're going to plug in 6.
Yeah.
So we're going to do f of b. Think of, this is our derivative. This is f prime. This is f. And then we're going to do f of 6 minus f of 4. So 4 times 6, 24, plus 36, minus 4 times 4, 16, plus 16. Yay. Took too long? It's fine. 20. It's okay. It's okay. It's not a speed contest. All right, what's the antiderivative for e to the x? E to the x. Good. So e to the x. And we want to evaluate this from -1 to e. So we get e to the e minus 1 over e. And that's all. You don't have to find a common denominator in a book. That's all. Just stop. Okay. You want to try the next two on that phone? Sure. Let me freeze them. You can try these two. Oh, you can do this in your head because this. Yes. Here, look. 81 fourths minus 1 fourth is 80 fourths, which is 20. Oh. Plus 3 is 23.
81 over 4
Minus
plus 3.
Wait, can you divide 81 by 4?
No, don't listen. Don't try to sorry. Don't make more work for yourself because if you have 81 fourths plus 3, and then what happens when I plug in this? I get 1 4.
1 fourth minus 1.
Yeah, negative.
I could combine those to make it 80 fourths, which is 3.
Oh, wait.
It would be negative 5. Negative 3 fourths.
What? No, because it's an even power.
Oh, yeah.
Okay, 4 to the 5 halves. Make sure that you're writing it like if you have 4 to the 5 halves, we're going to write it as the square root of 4 to the 5th power. So take the root first, it's so much easier, and then the power.
Right. Plus 2 over 4. Yeah. 96 over 4.
Yeah.
which is 1 away from 100. So it's 24.
Okay,
Unit is 0.
Commutative property says we can add. Oh, I didn't put the other part. Sorry. I was just focusing on the fractions. There's. I don't remember what the other part was. What was it? Minus 2 or plus 1. What did you get for?
Oh,
So then try D.
That's what I got.
2 over 5.
Wait, what's
x to 5
the
halves.
64.
Is it 64?
Yeah. 24.
Then a square x to the, so square root of x.
Yeah,
24 is the
Let's
same
get there.
as
Square root of x to the fifth
Yeah.
for D. Is it
Uh-huh.
that?
2/5 x to the 5 halves.
So
Yeah,
the
that's
square root of x.
Yeah, so for this one, again, you're gonna have a lot of rational exponents, so maybe you need to go back and review, maybe not, but just always make sure to do the root first, because you don't want to do 4 to the 5th power and then take the square root, because you're not gonna have a calculator for a problem like this. So you're gonna want to do the root first and then to the power.
64 over 5.
Okay. Is E? I don't know. Let's see. Yeah, sure.
2 power 5.
Okay, so if it's the integral of negative sign, it's going to become
32 times
positive
2 is
cosine?
64 over 5.
So cosine of theta.
That's just 0. That's the answer, right? That's just 0. 64 over 5.
Yeah, that's just 0. 64 over 5.
That's what I got.
Good job. All right, back to our unit circle.
Negative
So
root 3 over
cosine of 5 pi. Great, so your unit circle, right, here's 5 pi over 6, here's pi over 6. It's a longer x.
Oh, negative. It's root 3 over
Negative
2.
root 3 over
yeah.
2. Minus, well, cosine of pi over 6 would just be root 3 over 2. And when we combine those, okay, last one of these, and then the last page will be quick. Okay, so there is a method that we can do this. It's the composition of functions, so it's called use substitution, which we don't get to yet. So in the meantime, instead of that, we have to multiply this out, and then we can do the power rule. So just multiply the x plus 1 squared out before we integrate. So it's going to be x squared plus 2x plus 1. Yeah. And then just do each part. So what's that going to be? X cubed over 3 plus x squared plus x. Oops, why did I switch those? So plug in 0, the whole thing's going to be 0. So it's going to be what? Negative 1/3 plus 1 minus 1.
Oh, I forgot
Yeah,
about
pause it.
0.
Ah. So
1/3.
you don't need to put the 0 in front. I think it's helpful though, because if you don't put the 0 as kind of a placeholder, sometimes you forget that you're subtracting this whole thing.
Look, when you told us how to do it, I did it by just like doing the power rule with the whole x plus 1.
Okay.
1/3 anyway. Yeah, I just did it.
Okay. So be very careful. This will work.
Some of the time and all.
Not, yeah. So if it's x plus 1, what is it, squared? You're right. You could do x plus 1 to the 3rd over 3. The only time you can ever do this is if the derivative of the inside is 1.
So, for example, if it was 2x plus 1 squared, and you put 2x plus 1 to the third over 3, so okay, so does that make sense, Trevor? So it just so happened it worked out if you did the power rule with this.
No, because he said he didn't practice.
Did he say why?
Oh.
Oh. Okay.
Well, he's been isolated.
All right, finding total area. Moving right along. Okay, so we know integrals can sometimes turn out to be negative. If I were to integrate this whole region, this would be a positive integral, but this area under the curve would count as a negative. So what if I just wanted the total area instead of just the integral from here to here? I have to do the area. What's that? I want total area, not just the integral. So I want you to understand when it goes below the x-axis, the area, hold on, the area is not equal to the total area that is bounded by the x-axis in the curve, because this will count as a negative if I just do the integral, okay? But now what I want to do is I want to split it up. So first of all, I want to figure out what are the zeros. So where is 3x squared minus 3 equal to 0? X is plus or minus 1. So here, x is negative 1. Here, x is positive 1. Okay, so what we're going to do is we want to integrate each subinterval. So from -2 to -1, -1 to 1, and 1 to 2. And then we're going to take the absolute value of the integrals. Now, technically, we only have to do one absolute value. And that would be for this one here.
You don't know that.
Well,
You didn't give us the function. You didn't give us the
okay, if I just gave you the graph, you would have to graph this and figure out where it goes below the x-axis. But I gave you the graph, so you should be able to see it.
No, yeah. But I mean, like, if you just give us the function, you want us to graph it.
Yeah. If you know the graph is all above the x-axis, it's not an issue. So take, for example, what if I gave you, from 1 to 8 of e to the x? Like if I said the area, none of it goes below the x-axis, so my area is equal to the integral. But if I give you something that goes below the x-axis, then that's not going to work out. Okay, so we're going to partition it. So now we want to find the area. So we're going to take from -2 to -1 of 3x squared minus 3 dx plus the integral from -1 to 1 of 3x squared minus 3 dx. That I'm putting in absolute value plus the integral from 1 to 2. Now that's a lot of work, but we have some nice symmetry going on, so we can actually reduce some of the work here. These two are the same area. Now, I could either evaluate this one or I can double this one. I would probably double this one just because we have positive limits of integration. I mean, negatives are fine. It's just sometimes it's easier here. So why don't we? So we're going to double. Let's integrate this. So this would be 3x cubed over 3. So x cubed minus 3x evaluated from 1 to 2. So that'll take care of this and this, these two regions. Just because it has symmetry, if it wasn't symmetric, we wouldn't be able to do that. And if you're afraid you're dividing it up, just keep them all separate then. You'll get the same answer. This is just if we can make some of this work a little bit easier. And what else can we do?
Don't you use the absolute value, the integral of minus 21?
Yes.
Oh.
I don't know, do you use a different symbol?
No, it's the same. It's just,
Oh, maybe I should have used a different color.
yeah.
Also, did we notice here, there's symmetry going on here?
Mm-hmm.
So I could also double the area from 0 to 1. Why would that make it easier?
Yeah, right.
Oh, because if one of the limits of integration is zero, it's a lot easier to evaluate. So let's make this a plus. Oops. Stop. Stop. We'll get used to this because when we get to next chapter, in chapter 7 and 8, when we work with areas, anytime there's symmetry, you want to like make it as simple as possible. So you want to double areas whenever you have that symmetry. Okay, now let's evaluate it. Let's see. What's that end up with? Plug in 2. So that'll be 8 minus 6. Plug in 1. What's that? 1 minus 3. And then here we'll have, let's see, 1 minus 3. But we want to make sure we take the absolute value of that. 4, so 2 times 4, so we get 8 plus 8 plus 4. So it's about good. All that just to get 12. But still, that's a significant result. Like, this is not a regular area. You couldn't have done this. They look like triangles, but they're not, right? This area and this area, it's still curved. And this is in a semicircle, so we don't have a formula other than integrating using, you know.
Why are you not like subtracting what I thought? Why don't you do minus absolute value?
You're trying to find the area.
We want to find the area. So that's what I was trying to explain earlier. The area is not equal to just this to this. We want to split it up because wherever it goes below the x-axis, we want to make that positive. Okay, now there's a super easy way to do this on our calculators.
Wait, what if it was above the x-axis?
So if it was all above the x-axis, then the area is equal to the integral. Okay, so if you knew everything was above the x-axis, you can just do the integral. Yeah. But if it goes below the x-axis at any point, we have to split it up into parts. Or if you have a calculator, you can just type it in. So if you just type it in, remember the integral is here. It's next to the little catalog book. You can also do menu calculus. And then we have to calculators maybe. And then the absolute value. Start here, next to the catalog. Or you can go to menu calculus. All right, do you see the integral sign? Right here. And then you see
Wait, do you do the absolute value?
okay, absolute value is in that same area. The bottom left. Oh, no.
I got 12.
That's an integral.
Oh.
That's an indefinite integral, but you can't use it here.
Yes.
Degrees versus radians don't matter here, but if it was If it was a trig function or something, we would want to make sure it's in radians. Okay. All right. Any